Are we good?
Yep, that sounds
Okay,
good.
perfect. Well, hello everyone. Welcome to my talk on T-Rex. My name is Ref. I'm a physics master student here at Brown. Today I'm going to be discussing a satellite mission proposal that we're developing to capture the first movie of a black hole. The black hole in question here is Sagittarius A star, which is the black hole at the center of our Milky Way. So this is going to be hopefully an exciting talk. If you have any questions, please feel free to unmute, just ask away. Um, this is literally rocket science, so there are no dumb questions at all. Okay, with that being said, let me just give an overview of what this presentation is going to be. First, I'm going to introduce what the team looks like, the T-Rex team, and then we'll get started on the primary science objectives of this proposed satellite mission. And then we'll discuss, since this is a data science workshop, I'll try to show you how we actually simulate observations of Sagittarius A star using T-Rex. So to justify putting a satellite out into space, you need to create simulations that show that anything you capture from space will be much better than things you capture from the Earth, right? Images you capture from the Earth. So I'll show you guys how to create a basic simulation using Python. Um, for T-Rex. And then we'll discuss some of the mission parameters for the T-Rex mission. And then finally, I'll conclude with some exciting simulations that we've developed here that show what kind of a movie we might expect for Sagittarius A star. So again, feel free to ask away with any questions. I know a lot of folks in the audience might not be familiar with black holes, so you can ask any questions about that as well. So anyway, my name is Ref. I'm a physics master's at Brown. I work in the applied math department on binary black holes on the LISA mission. And T-Rex was originally a part of Brown's satellite development group, which has launched 3 satellites in the past. T-Rex is an acronym for the Time Resolving Explorer satellite. It's so called because the goal of T-Rex is to capture movies of the night sky as opposed to pictures. So we want to see how things that evolve dynamically, if we can time resolve them over time with this radio satellite. So the T-Rex team is made of about 10 students, half undergrad, half grad students. And the primary science objectives of the mission are as follows. So the main focus of the T-Rex mission is to look at supermassive black holes. The primary science objective of the mission is to capture the first movie of Sagittarius A star. Um, Folks in the audience may have seen the first image of a black hole in 2019. It looks like a donut. However, it's very difficult to capture a movie of a black hole from the ground because the ability to capture images, the rate at which you capture images from the ground, is limited by the rotational period of the Earth. So if you can put something into low Earth orbit that orbits the Earth rapidly, the idea is that it can capture images much faster and then sequence those images into a movie. So this is the basic idea for T-Rex. So this is the primary science objective, to capture the first movie of Sagittarius A star. Um, Feel free to ask any questions if you have any. Um, the secondary science objective is to look at 2 black holes, binary black hole systems, and try to capture the first movie of a binary system. Now, this is even more challenging in some respects than a single black hole, because if you have a binary black hole system, you have to individually resolve each of the component black holes and see how they evolve over time. Um, so this requires exquisite angular resolution, about 20 times better than what was achieved by the Event Horizon Telescope in 2019. So this is a massive engineering and technical challenge, but we hope to achieve this for our secondary science objective. And finally, the tertiary science objective for T-Rex is to look at many supermassive black holes in other galaxies. These black holes are much smaller in our night sky than Sagittarius A star because they're much further away. But nonetheless, T-Rex hopes to look at these black holes in the radio domain at 86 gigahertz, about 3.5 millimeters observing wavelength. And the hope is that by looking at these other black holes, we can do some kind of a population study on the mass and spin of black holes across many different galaxies, as opposed to just our Milky Way. So these are the 3 primary science objectives for T-Rex. Um, and let me now move on to the main relevance of T-Rex for NASA. So NASA has outlined their priorities for the upcoming decade in the Decadal Science Survey. And one of NASA's kind of tentative goals is to establish a time domain program. A time domain program is dedicated to launching space missions that can capture movies of the night sky, that can see how things evolve over time. We're talking about things that change rapidly in the night sky on the order of seconds, minutes, or hours. Um, so this is opposed to many flagship telescopes that are already out there, such as Hubble or JWST, which can capture exquisite pictures, but not necessarily movies in the night sky. So T-Rex in particular would capture radio domain movies of black holes in particular, hence its relevance to the time domain program. Um, so what would a movie of a black hole look like? What does that mean? So that to explain that, I'm going to actually skip to slide 97, which is going to explain what exactly is a black hole. So I know some of the folks in the audience may not know what a black hole is. So let's start off with the basics. So a black hole is this remarkable prediction of general relativity that predicts that you have some kind of an object in space where you have an event horizon, you have this boundary. And if you cross this boundary, if you cross the event horizon of a black hole, there's no way you can escape. This is the only known object in the universe that has this unique boundary-like feature. Even light, the fastest object in the universe, once it trespasses the event horizon, is doomed to fall into the singularity of a black hole. Now, black holes have several other interesting geometrical feature. Um, I'll explain these so that you can understand what the first image of a black hole is showing and how we can capture images of a black hole. Um, so outside of the event horizon of a black hole is what's called a photon sphere. This is the last orbit that photons can make around a black hole. Um, and then just outside the photon ring is what's called a black hole shadow. This is essentially the last, when if you shoot photons, if you shoot a ray of light at the black hole, it would come in at the black hole shadow, get pulled in by the gravitational pull of the black hole, and then just graze the photon ring. So it wouldn't trespass inside the photon ring because then it would fall in, but it would just graze the photon ring and then come back out. So what does that actually look like in terms of an animation? Um, okay, let me just skip all the math here. Okay, so in terms of an animation, this is what happens when you throw light at a black hole. If you try to capture an image of a black hole, this is what would happen to the photons you send in. So the light would come in at a radius. That's the radius of the black hole shadow, and then you can see the light rays actually bend inwards as they're pulled in by the gravity of the black hole. And so they're pulled in, and then ultimately they go back out to the black hole shadow radius. So this is the trajectory of a light beam, or lots of light beams that are thrown at a black hole. And so when we look at the first ever image of a black hole, what we're actually seeing inside is not the event horizon, but it's something just a bit bigger than the event horizon, which is the black hole shadow. So that's this inner circle you're seeing right here. And then this orange blob encircling the black hole shadow is the accretion disk of the black hole. It's the accretion disk of the black hole, which consists of matter, dust, and gas that's circling around the black hole at relativistic speeds. Um, so yeah, so this is what you're looking at when you see the first ever picture of a black hole. Um, Let me just pause here. If there's any questions in the audience, feel free to unmute, ask away. I know this is a lot at once. Okay, well, if not, so let me proceed. So now that we know the geometry of a black hole, its event horizon, its singularity, the photon sphere, the black hole shadow, how do you actually image a black hole? How do you take a picture of one? How was it taken in 2019? And how does T-Rex hope to take that into space? So this is the first ever image of a black hole released on April 10, 2019, captured by the Event Horizon Telescope. And the way that this image was captured was as follows. To capture an image of a black hole, it turns out you need a very, very large telescope. Why is that? Well, black holes are very tiny objects in the night sky. Even though in reality, black holes are huge, supermassive, gigantic objects, you could fit our entire solar system inside of the black hole at the center of our Milky Way. But the problem is that the black hole is very far away. So even though it's very large in reality, its distance makes it very compact on the night sky. So in particular, the black hole at the center of our Milky Way is about 30,000 light years away. And so that means if you look at it in the night sky, it's about 1 billion times smaller than the size of Jupiter. It's akin to taking an image of a donut on the moon. So that's how difficult it is to capture an image of a black hole. You need a very big telescope because what you're trying to image is very small. It's very compact on the night sky. Now, the problem is, it turns out the actual diameter of the telescope you need is the same as the diameter of the Earth. So the numbers work out just right so that you need a telescope the size of the Earth to image Sagittarius A star. Now, this is not possible. So, not least because of NSF funding nowadays, but the alternative approach is something called interferometry. Instead of one big telescope the size of the Earth, you can use many small telescopes and combine their data. And so that's the approach that the Event Horizon Telescope collaboration used in 2019. So the idea is you have many telescopes combining their radio data into a single coherent picture. Now the next question is, why do you use radio telescopes? Why can't you just take out an optical camera? Why can't you just take your iPhone and snap a picture of Sagittarius A star? And the reason is because of what's known as the spectral energy distribution of the black hole. This tells you where is the black hole brightest. So black holes are emitting light at many different wavelengths. But the wavelength at which they're brightest is in the radio domain. It's around 230 gigahertz, which is about 1.33 millimeters, if there's any optical folks in the audience. So what that means is that if you want to take an image of a black hole, you should probably use telescopes that operate at the same frequency where the black hole is brightest. And so that's why the Event Horizon Telescope operates at 230 gigahertz, because that's simply where the black hole is most luminous. But then there's another problem. So you've got all of these telescopes, they're all observing at the same frequency, they're all looking at the black hole at the same time, but now you've got another problem, which is the atmosphere. The Earth's atmosphere can add noise to your image of the black hole. So you have to pick just the right frequency so that the Earth's atmosphere causes the minimum amount of disruption, minimum amount of noise to your image. And so there are what are called atmospheric windows in the Earth's atmosphere that have the least amount of interference. And so that's another reason why the first image of a black hole was taken at 230 gigahertz. It's because the Earth's atmosphere is largely transparent at those frequencies. So you don't have to worry about it as much. So now the next question is, if you'd like to image the black hole at the center of the galaxy, how far apart do you have to place your radio telescopes? And to answer that question, you need to look at the black hole and the size of the black hole. The size of Sagittarius A star is about 1 billion times smaller than Jupiter, 50 microarcseconds in diameter. And so that means you need to be placing your radio telescopes as far apart as the diameter of the Earth, about 12,000 kilometers apart. And so that's what you see in this illustration here. If you'd like to image a black hole, you need to be putting your radio telescopes as far apart as possible, spanning the entire diameter of the globe. Okay, so those are all of the challenges for imaging a black hole from the Earth. But now, to make matters worse, there's another challenge, which is something called scattering. Scattering is the idea that between us on the Earth and the black hole at the center of the galaxy, there's a lot of dust, gas, and plasma that's going to introduce noise into the image. And so even if you didn't have an atmosphere for the Earth, even if you had no atmospheric noise, you had telescopes spread all the way around the Earth, and you were able to take a perfect image of the black hole. Scattering between us and the black hole would actually blur the image so that it goes from this to something like a blob. So scattering is a major problem for the black hole at the center of our galaxy. And not as much of a problem for other black holes because they're not obscured by galactic dust and the interstellar medium. But for the black hole at the center of our Milky Way, this is a major challenge, not only for ground telescopes, but also for space telescopes. Okay, and let me just skip the other complications. So basically, it's hard. It's complicated to take an image of a black hole. There's a lot of things you have to worry about. You have to worry about where is the black hole brightest? Where is the Earth's atmosphere least opaque? How far apart do I have to put my radio telescopes? What about the problem of scattering? That's going to introduce noise into my image. So you've got all of these problems that you have to worry about when you try to image a black hole from the Earth. Um, so now what I'm going to do is talk about briefly what the pipeline is for capturing an image. We talked about some of the challenges, but if you're able to surpass all of these challenges, how do you actually capture an image of the black hole? So this is how. The first goal, the first thing we have to do is have some true image of the black hole. Now, what do I mean by true image? Well, Einstein's equations of general relativity predicted the existence of black holes all the way back in 1915. And so if you solve Einstein's equations on a computer, you can get some kind of a prediction for what a black hole would look like if there was no noise, no atmosphere, no scattering. In other words, if you had a perfect telescope with infinite resolution, infinite capabilities, what would a black hole look like according to Einstein's equations? So we have some kind of a true model of the black hole, some kind of synthetically generated model of the black hole on our computer. And then what we do is we construct an array of telescopes. So we say, okay, I'm going to observe this black hole with these three telescopes, for example. Um, so that's what you put in your simulation. You have this observing array, you have this true model, and then the result of the simulation will be something called a UV coverage plot. This UV coverage plot, this is just jargon. What it really is telling you is how much radio data are your telescopes taking of the black hole. So let me, okay, well, okay, this was an analogy to explain UV coverage, but I'm going to skip that. The idea for UV coverage is that the more you fill in this plot, the better your image of the black hole. The more radio signals you get, the more filled up this circle will be with blue points, and the better your reconstructed image of the black hole. So the idea is that this UV coverage plot really holds the key to imaging a black hole. This is the end all be all. If you want, if the Earth was filled with telescopes, you would have 100% radio coverage of the black hole. And so what you would do then is do an inverse Fourier transform to recover a reconstructed image of the source of Sagittarius A star. But in reality, we don't have infinite telescopes, and so there is sparse coverage of the UV plane of the black hole on this Fourier domain. So this is the basic pipeline for imaging a black hole with radio telescopes. Let me just pause here. If there's any questions, concerns, comments, feel free to unmute if you have any questions. But if not, let me proceed then to how T-Rex will take the first image of the first movie of a black hole from space and try to alleviate some of the challenges I just mentioned. So this is what a black hole would look like if we had an infinite resolution camera. So this is what's called a GRMHD, general relativistic magnetohydrodynamic, whatever. It's just some jargon that means that we solve Einstein's equations on a computer. And if we solve Einstein's equations on a computer, this is the predicted movie of a black hole. If you had perfect angular resolution, a perfect telescope, no scattering, no thermal noise, no atmosphere, this is what a movie of a black hole would look like, ideally. What you're looking at here is what's called the accretion disk of the black hole. Hot dust, matter, and gas that got swept up by the gravitational pull of the black hole. And you can see that if we capture a movie of a black hole, we can see what direction the black hole is spinning. So for example, in this movie, we're seeing that Sagittarius A star is spinning what, counterclockwise? I can't quite tell clockwise from counterclockwise. But the basic idea is that from a movie, we can constrain the spin of the black hole. And that would be the first constraint on the spin of Sagittarius A star. Um, okay, good. Now, this is a perfect movie of Sagittarius A star if you had no challenges. But in reality, this is what a movie would, this is what a more realistic movie would look like using a telescope like T-Rex. So what you're looking at here is the following. So on the left-hand side, we have some kind of a true model, a very crude true model of Sagittarius A star. Um, the event horizon of the black hole is depicted by this ring-like structure, and then we have a hot spot that's orbiting the black hole with some orbital period. So this is the ground truth. And then after we observe the black hole with our observing array, this is what the movie would look like. So you can see that scattering does a lot of damage to the movie. You can no longer resolve the ring-like structure of the black hole at the center, but you can just make out this orbiting hotspot. Now, this is at an observing frequency of 86 gigahertz. What does that mean? 86 gigahertz means that your telescope is sensitive to high frequency radio wavelength light. But if you go to even higher observing frequencies, up to 150 gigahertz, then your movie becomes like this. So what's going on here? What's the difference between these two movies of the black hole? Well, you can see that at a higher observing frequency, you can begin to resolve the ring-like structure of the event horizon, right? And so why is that possible? That's possible because interstellar scattering is less intense at higher observing frequencies. In fact, it goes down as observing frequency squared. So if you double your observing frequency, scattering drops by a factor of 4. Hence the,
Um,
oh,
I
yeah,
have, sorry, I have a question.
yeah, yeah.
The observing frequency, is that like the frequency of light that you're looking at, or like what frequency, what frequency is it actually?
Yes, yes. So observing frequency is what frequency of light is your antenna, is your radio telescope most sensitive to. And what that really comes down to is so every antenna is designed to operate at a different frequency. Antennas have what's called a horn but behind them. That antenna horn is responsible for making sure the antenna has the right surface accuracy, the right surface error to operate at that frequency. So for example, if you have an antenna that's designed to operate only at 86 gigahertz, it cannot capture any light. It's going to be basically insensitive to light from the black hole that's coming at higher frequencies, like 150 gigahertz. So basically, this number tells you what light is your telescope most sensitive to. Um, and
Okay.
higher, oh, sorry, Aspen, yeah.
Oh, just that makes sense. Thank you.
Okay, great, great. And higher observing frequencies, so even though it looks like higher observing frequencies are better, they're actually more challenging to operate at because higher observing frequencies require better surface accuracy and lower surface error for your antenna. So everything comes with a trade-off in space telescope mission design, and this is no different. So even though the movie of the black hole would be better at higher observing frequencies, we believe that it would actually break the swap requirements, the total cost budget for the satellite if we were to operate at 150 gigahertz as opposed to 86 gigahertz. Um,
I have
now,
another question
yes,
before
yes,
you go
please.
on.
Mhm.
This revolving like the bright spot, is
Mhm.
that like an actual artifact of the black hole, or is that because of the way that you are observing it? Like, is there actually some kind of like bolus of material that is circulating in this black hole?
Yeah, so that's a great question. So I'm going to divide your question into two separate questions. First of all, is this a real kind of hotspot orbiting the black hole? And if it is, then what even is that? So first, let me start by the second question. So so there are many different models for Sagittarius A star, the black hole at the center of our galaxy. We don't actually know what it looks like in terms of a movie. We have the first picture of Sagittarius A star, which looks something like this. It looks like a donut, something like this. But it's actually unknown where these blobs are originating from because they could be originating from a combination of two things. These could be actual dust, gas, matter that's orbiting the black hole, or it could be light from behind the black hole being gravitationally lensed. So this could actually be something that's not around the black hole, but rather behind the black hole that's being curved by the gravity of the black hole and entering our lens. So at the moment, it's unknown whether these hotspots are real hotspots that are native to the black hole's accretion disk, or if they're false positives, if they're something behind the black hole that's being gravitationally lensed. Um, so that's one thing. But if these are actual hotspots, so a movie of a black hole, for example, could resolve this discrepancy. Why? Because if it is a real hotspot, it'll have a different orbital period than if it were something that were gravitationally lensed behind a black hole. Um, so these hotspots are basically, if they are true, if they are around Sagittarius A star, these are basically clumps of gas and mass plasma that have clumped together and start orbiting the black hole. They're they're completely different, but one way you can think of it is something like sunspots around the sun. Um, so these hotspots are basically clumps of gas and dust that are orbiting the black hole. But we are not actually sure if they're present around Sagittarius A star. Um, it would take a movie of a black hole to really resolve these hotspots in the accretion disk if they exist. Does that answer your question, Aspen?
Yeah, absolutely. Thank you.
Yeah. There's another, actually, I'm going to forget this, but there's another very interesting feature of Sagittarius A star, which is it releases flares. So just like the sun releases solar flares, Sagittarius A star has actually been observed to release infrared flares that flow away from the black hole. So this is basically dust and gas that are ejected from the accretion disk. At relativistic speeds away from the black hole. These have been picked up for the first time. Um, let me just very briefly show that. These have been picked up for the first time by the Event Horizon Telescope collaboration just recently, last year. Um, and one possibility is that a movie of a black hole would ideally be able to see these infrared flares as well. But the problem is that these infrared flares might be less bright in the radio regime that T-Rex operates at. Um, so yeah, so black holes have a lot of interesting geometry. They have hotspots, they have flares, they have these accretion disks. Um, so yeah, so a movie of a black hole would shed light into all of these dynamics. Um, Okay, so I promised that I would explain this idea of UV coverage. So the idea of UV coverage is really central to capturing a movie of a black hole. So it's worthy of further explanation. So let me zoom in here. So what are you looking at here? This is a plot of, this plot might look very complicated, but the idea is very simple. You have a red circle that denotes Sagittarius A star, the black hole at the center of our Milky Way. And every blue dot in this red circle is a single radio observation of Sagittarius A star. The more blue dots you have here, the better. The best case scenario is that you have telescopes all around the world and they completely fill up this circle with blue dots. Well, I can't make it blue. Zoom is not letting me. But the basic idea is the more you fill up this circle, the better your image of the black hole or movie of the black hole. Now, here's the dramatic difference when you put something in space. If you're observing Sagittarius A star only with ground telescopes, you can see, so ground telescopes, this is denoted by EHT, the Event Horizon Telescope. So you can see, observing only with the EHT, you achieve 20% radio coverage of Sagittarius A star in 30 minutes. Okay, so that means you get 20% of the radio signals emanating from the black hole in 30 minutes if you just use ground telescopes. But If you add just one satellite in low Earth orbit, this is the dramatic difference it makes. Your radio coverage jumps to about 56%. Now, okay, this doesn't have any meaning. What does that even mean that your radio coverage jumps to 56%? So here's what this means in terms of an actual image. So if you observe Sagittarius A star only with ground telescopes for 30 minutes, this is what 20% radio coverage looks like. You get a kind of worse, a much worse version of the donut image from 2019. But if you add just one satellite in low Earth orbit, this is the difference it makes. In just 30 minutes, your radio coverage jumps to about 50%, and you can start to resolve the hotspots around the accretion disk of the black hole. So, so this is the visual difference that adding a satellite in space makes to capturing a movie of a black hole. You can start to resolve finer scale structure around the black hole. So let me just skip through these. These are more technical slides. I want to talk a little bit now about the cost, the size, and the weight of this proposed T-REX mission. So T-REX, let me first go to this. T-REX is a proposed radio satellite. And so what that means is it has this giant antenna, and behind that antenna is all the infrastructure supporting the satellite. So the main components of T-REX are as follows. You have an antenna. This is the main component of the satellite. The entire thing is basically a flying antenna. But behind the antenna is the receiver that's responsible for capturing those signals, the radio signals coming from the black hole. The receiver has to be kept very cold so that it doesn't emit thermal noise that disrupts the signal. So we need a cryocooler to cool down the receiver to about 25 degrees Kelvin. Now, you need to know exactly when the radio signal hits your antenna if you want to combine it with radio signals from other telescopes. So we also need a very stable clock on board the satellite. This is what's known as an ultra-stable oscillator. So you can see all of the work that goes into building a satellite. You need an antenna to capture the signals, to funnel them into the receiver. The receiver has to be very cold. You need a cryocooler. The receiver needs to know exactly when the signals are arriving. So you need an oscillator, a clock. And finally, once you have all the data, you need to send it down to the Earth somehow. And so we need lasers to send data down to the Earth. So this is what's known as the optical terminal. The optical terminal will send a laser signal down to the Earth, and the data will be captured at some receiving station down on the Earth. So each of these T-REX satellites are expected to be about 100 kilograms for payload alone. And they're expected to cost about $30 million. So T-REX, the proposed mission, is not one satellite, not one radio satellite, but three radio satellites arranged in a triangle in space. So let me actually first show what T-REX, let me skip these slides just for a moment. So this is the basic concept for T-REX. You'll be seeing this animation loop in a moment. But the basic idea is that you have three satellites, three of these radio satellites arranged in a triangular configuration around the Earth. And these three satellites are all observing Sagittarius A star, the black hole at the center of our galaxy. So you'll see that pop up right here. So Sagittarius A star is emitting radio signals, and these three satellites are picking them up. Okay, so that's number one. And then we'll have a very small satellite. It's barely a satellite. It's known as a DiscSat. DiscSats are these relatively new satellite structures that look like circular discs. They're very compact, very small, not very costly. And so the DiscSat will receive the radio signals. It'll receive the data coming in from each of the three T-REX satellites. And the DiscSat will then downlink. It'll then send all of that data down to the Earth. So I'm going to show this animation one more time. So the data, the radio signals are coming into the T-REX satellites from the black hole. The satellites send their info up to the DiscSat, which correlates the signals, combines them in space. And And then finally, once the DSCsat is at the top of its orbit, it will downlink the data down to the Earth. It's going to send the data using a laser optical downlink. So you'll see that happen in hopefully just a minute. So the DSCsat is receiving the signals, and then it will hopefully now downlink to a ground receiver, which is what you're seeing right here. So this is the basic premise of the T-Rex mission. You have a triangular configuration of 3 radio satellites that are receiving radio signals from the black hole at the center of the Milky Way. These 3 satellites then send their data to a DSCsat, which will correlate the data, combine the data on orbit, and then send that data down to a ground receiver on the Earth. So, okay, good. First of all, that I know this was a lot to take in. Do we have any questions about the DSCsats, the orbital configuration, what's really going on in this animation? Feel free to ask away. Okay, well, if not, let me describe, since this is a DSCoV talk, let me explain a little bit about how to create simulated observations of Sagittarius A star using T-Rex. So here's the basic idea. If you want to create an image of a black hole or a movie of a black hole using T-Rex, if you want to validate this mission concept, how would you go about doing it? So here's the basic idea. The first step in the process is to have a ground truth. Unfortunately, I don't have that depicted here, but you have some kind of ground truth of how the black hole would really look like if you had a perfect telescope, infinite resolution. So the way you get this ground truth is you solve Einstein's equations on a computer numerically, right? So this is your ground truth, your source model. And then just like we saw before, you have some kind of observing array. You specify that you'd like to observe this ground truth with 3 satellites, let's say. Okay. So once you specify your ground truth and your observing array, our simulation will produce some UV coverage plot. The UV coverage plot, the only thing it tells you is how much radio signals do you get of the black hole. If we lived in a perfect world, this is what your UV coverage plot would look like. It'll look like a perfect filled-in circle. In reality, of course, the UV coverage plot consists of discrete points, simply because we don't have infinite telescopes. But once you have your UV coverage plot, what you can then do is essentially a Fourier transform of the UV coverage plot. And that gets you something called a dirty beam. This dirty beam basically tells you what is the response of your observing array of your 3 telescopes to a point source on the night sky. In other words, if you take your 3 telescopes and you look at a single point, a point source on the night sky, what would your telescope see? That's what the dirty beam answers. The dirty beam tells you the response of your satellites to a single dot in the night sky. Okay? So then you take your dirty beam and you take your true ground truth, your source model, your ground truth that we talked about, the very first step, and you convolve these two. You multiply them. So you convolve your dirty beam with your true sky brightness. And what you get is what's called the dirty image. And so this is what your telescope would really see. So for example, oh, we have something in the chat. Oh, okay. Great. So for example, what are we looking at here? In this case, our ground truth is a galaxy and a point right here, like some kind of a star maybe. So what we do is we specify our observing array, we get our UV coverage plot, we take a Fourier transform to get the dirty beam, and then we take the convolution of the dirty beam with the true sky brightness that gets us the dirty image. And so you can see what the dirty image looks like compared to the real model. You can see the galaxy over here is now this blurry thing. And this point source, this star perhaps, is now this blurry circle right here. So this is the native image, the first look that your telescopes will have of the night sky. And then what you do is you take your dirty image and you feed it into an algorithm that tries to minimize some kind of a loss function between the true image and the dirty image. And the outcome of the algorithm is what's called a clean image. And so this clean image is your predicted reconstruction of the night sky after your radio telescopes look at the source. So this is the basic pipeline for imaging a black hole. You have some kind of UV coverage that tells you how much radio signals you're able to capture. You take the Fourier transform to get the dirty beam. The dirty beam is the response of your interferometer, of your radio telescope, to a single point source. You convolve your dirty beam with the true image of the night sky, and then you get a dirty image, which you can then feed into some kind of a optimization algorithm that gives you a clean image of what you expect the night sky to be once you image it. So are there any questions about this pipeline? Because now I'm going to actually show you how to simulate this for T-Rex. I know this was a lot, so feel free to shoot any questions. It can also be questions about other aspects of the talk, like black holes or the mission parameters for T-Rex. Okay, well, here is how we go about simulating T-Rex. So the first thing we do, I'll be using a library called EHT imaging. EHT stands for Event Horizon Telescope. The first thing we'll do is we'll specify the orbital altitudes of the 3 satellites. So in this case, in this simulation that I'm about to show you, I've got a very simple orbital altitude configuration. One of the satellites is at 600 kilometers away from the Earth. One is 640. One is 620 kilometers away from the Earth. I made a typo here. This 600 kilometers is the distance from the surface of the Earth to the satellite. If this does not add on to the radius of the Earth, which is 6,000 kilometers. Anyway, so first thing we do is specify the altitudes of our 3 satellites for T-Rex. The next thing we do is specify our orbital inclination. So T-Rex needs to have a relatively high orbital inclination. And the reason why is because at higher altitudes, you can actually get better polar ground coverage. So what that means is that you can send data down to the Earth more often if you're at a higher orbit as opposed to if you're at a lower orbit. Higher orbits also offer better observational coverage of the black hole. So you can see the black hole more often from higher orbits than for lower orbits. Because at lower orbits, the Earth can actually obscure. You can actually get eclipsed by the Earth. If your satellite goes behind of the Earth, you can no longer see the black hole, right? And so we need a high orbital inclination, greater than about 80 degrees for T-Rex, for each of the 3 satellites. The next question is the eccentricity of the orbits. Eccentricity simply refers to how circular the orbits are. So in our case, all of the 3 T-Rex satellites will be on circular orbits, so eccentricity is 0. And finally, RAN, I have no idea, I forgot what RAN even stands for, but basically it's what is the angular displacement between each of your 3 satellites. So here I wanted to create a very simple simulation. So I said that the angular displacement between each of the 3 satellites was 120 degrees. So each of the 3 satellites are kind of equally displaced around the Earth. Okay, so once you do that, you would get something like this. You would have 3 equally displaced satellites receiving the radio signals from the black hole. They would then send their data to the DSCsat, which would correlate the data. Correlate means combine the data in orbit, which makes a dramatic difference in terms of data payload, how much data you have to store. And then finally, the DSCsat will send the data, beam it back down to the Earth via laser downlink. Okay, so we've already seen this animation before, but let me just wait for the downlink. Hopefully, there we go. Okay, great. So the next thing we have to do is specify where are we looking? Where is the black hole that we'd like to observe? And so we have to specify what is called RA, the right ascension, and dec, the declination of the black hole. This is basically the X and Y coordinates of the black hole. So we specify that. We specify our observing frequency, which is 86 gigahertz. Now, this actually brings me back to Aspen's question, which is, what does 86 gigahertz actually mean? And so it means what type of light is your telescope sensitive to, but it also tells you what can you see. So at higher observing frequency, you can actually see less of the black hole. What that means is the black hole becomes less bright, it becomes less luminous at higher observing frequencies. That's what you're seeing depicted here. Going from 10 gigahertz to 40 gigahertz to 200 gigahertz, you can see that at about 230 gigahertz, the optical depth of the accretion disk falls below 1. What does that mean? That means that the accretion disk of the black hole actually becomes invisible at 230 gigahertz, and the black hole overall becomes less luminous. So what's the benefit of higher observing frequencies? Well, you can actually probe closer to the horizon scale structure of the black hole. You can see that at lower frequencies, you can't even see the black hole. It's completely obscured by the accretion disk, by the jets. But at higher observing frequencies, you can begin to make out the black hole itself, and the stuff around the black hole becomes invisible. So this is the magic of the electromagnetic spectrum. At higher observing frequencies, black holes are less bright, and you can see closer to their event horizon, to their photon ring, to the black hole shadow, and so on and so forth. Now, T-Rex will be operating at 86 gigahertz because it's simply too challenging to observe at higher frequencies for us. Okay, and then the next thing you need to specify, okay, I think we're almost out of time, but let me just start wrapping up. The next thing we need to specify is the observation schedule for your satellites. So this is the observing schedule for T-Rex. In this simple simulation, we say that we begin our simulation at time is 0, end it at time is 24 hours, and then we co-observe. So the 3 satellites look at the black hole at the same time for only about 10 seconds in each interval. And these intervals are separated by 60 seconds. So what that means is that for this period of time, this 50 seconds, nothing is happening. The telescopes are not observing the black hole together. Why is that? Because in this period of time, the telescopes will actually be sending their data to the DSCsat. And in that period of time, the DSCsat will combine the data and send it back to the Earth. And so that's what this 50-second period is responsible for. So really the observing of the black hole happens in these 10-second, 10-second, 10-second outbursts that are separated by about 60 seconds. And then finally, we need to specify what is the minimum elevation of this elevation minimum tells you what is the point at which you stop observing the black hole from the ground telescopes. And so in this case, I specified 15 degrees. What does that mean? That means that if Sagittarius A star falls below 15 degrees from the perspective of the Earth's horizon, then ground telescopes can no longer observe the black hole. Why is that? Because the lower the black hole is on the Earth's horizon, the more atmosphere the radio signals have to pass through. And so there's usually a minimum elevation that you specify, where beyond that elevation, your telescopes basically cannot observe the black hole coherently. So once we specify all of these observing parameters, this is what the radio coverage for Sagittarius A star would look like, with 3 telescopes looking at Sagittarius A star, co-observing with a ground telescope. So what are we looking at here? We're looking at 3 T-Rex satellites. Each of these satellites are about 100 kilograms, costing about $30 million each. And these 3 satellites are co-observing with 1 ground telescope. This telescope is actually called ALMA in particular, the most powerful radio array on the Earth. And so you can see that as these 3 telescopes, as the 3 T-Rex satellites orbit the Earth, they receive more and more radio signals from the black hole. Now, this is a very simplistic simulation that does not account for several challenging factors such as data downlink, atmospheric constraints, integration time. But this is a basic idea of how 3 T-Rex satellites would co-observe Sagittarius A star. And so the way that I simulated this is we simply take EHTM. We say that we want to observe Sagittarius A star using our array. We specify the location of the source, Sgr A and declination. We specify our observation parameters. What's our integration time? What's our start and stop time? Remember, we specified all of this right over here. So all of this has already been done. We just need to plug it into this function, which will then give us our UV coverage. Um, Okay, so I think I am going to, I've got some more slides, but let me just stop it right here. Let me stop with this 3D model of T-Rex. And now in the last 5 minutes, I'm happy to take any questions, any comments, ideas. So yeah, feel free to unmute and question me away.
I have a couple questions. Um, so I'm curious, like, what is the status of this project? So I know that you applied for like NSF funding or you got NSF funding. So like, I guess where does this project stand right now? What are you planning on doing next? What are you doing at Brown?
Yeah, so T-Rex is in what's called pre-phase 1A. So it's very early in its developmental life cycle. The projected timescale for the T-Rex mission, if successful, would be about 12 years. And so we are in the second year of development. So this is very early on. T-Rex was selected as a NASA NIAC finalist last September. So we're waiting to hear back um, from NASA this March as to whether
Mm.
the mission will be selected for a phase one study. If it is selected for a phase one study, we'll have about a year to develop and prepare a phase one report on the progress of the mission. If it is not selected for a phase one study, we have several other grants that we're crossing our fingers for. And then the wild card in all of this is where I'll be going for my PhD in astronomy, which will tentatively fund the first 2 years of T-Rex. Uh, so yeah, so this is the
Yeah,
basic idea.
that makes sense. Which faculty member are you working with at Brown for this?
The institutional PI is Brendan Keith. So Professor Keith is my PI for the LISA mission, which is another gravitational wave mission. But he's in the applied math department.
Okay, yeah,
Yeah,
makes sense. Um, I'll see if anyone else has questions, and then I have and then I have more.
yeah, definitely. Um, this is literally rocket science, so please feel free to ask away. None of this stuff is obvious by any means, so please feel free to ask.
We have a question in the chat.
Oh, perfect. So Andy asked, just off the top of your head, would there be any benefit to having a satellite near the orbit height of the moon or really anything higher than medium Earth orbit? There absolutely would. And this is actually, so let me actually pull up a paper. Maybe I don't have time to pull up a paper, but basically, the further away you put a satellite, the better the angular resolution it has. So it can take better pictures if it's further away. At the same time, if you put a satellite further away, its movies will be worse. What does that mean? So the further apart your satellite is from the Earth, the better its angular resolution, the better its pictures, but the worse its temporal resolution. It can take pictures but at a slower rate. So that's the kind of trade-off we're operating in. You can put something as far away as you want, all the way up to the moon, but it would be able to take pictures perhaps once a day or so. If you put a satellite in medium Earth orbit, it can take a picture every 3 hours. If you put a single satellite in low Earth orbit, it can take a picture every 20 minutes or so. Um, so this is the basic trade-off that happens when you put things further away.
Is that because of the orbital period of the Earth, or like how fast it goes around the Earth? So like what if you put it in orbit on the moon? Like if you put it in orbit around the moon because the moon is smaller, would you be able to take like pictures more often?
Yeah, so that is a great question. So yes, so all of this boils down to let me see if I can pull this up. Okay, good. So all of this boils down to how fast. The big question is you want to capture a movie, then you got to fill this uh, Fourier coverage. You got to fill up this UV coverage plane as fast as possible. You can see here that as you add points, as you add radio signals to this UV coverage plot, the predicted image, I don't know why it's drawing a circle. The predicted image here is getting better and better as you add more points to the UV coverage plot. So if you put a satellite in orbit around the moon, um, it could potentially have better temporal resolution. Temporal resolution is only restricted by the orbital period of the satellite. So if you have a satellite that moves faster around the moon, then it can capture images faster. So the orbital period of any object is given by gm, square root of gm over r, where m is the mass of the host object. So the mass of the moon is much smaller than the mass of the Earth. I don't remember off the top of my head how much smaller, but the idea is that that means if you put an object at the same distance away from the moon as from the Earth, it would orbit the moon at a slower velocity because the moon is less massive. So that means you would have a lower temporal resolution if you put an object around the moon. But that being said, the moon is also smaller than the Earth. So you can actually get closer to the moon than you can get closer to the Earth. The Earth has some radius, 6,000 kilometers, and the closest you can get to the Earth is about 500 kilometers from the surface. Otherwise, atmospheric drag is going to take you down. On the other hand, even though the moon is less massive, so that your orbital velocity is lower at the same distance, even though the moon is less massive, it's also smaller. So you can also put your satellite closer to the moon, which means you can try to investigate this trade-off. Try to see how close you can put something to the moon. And if you can exceed the orbital velocity of a low Earth orbit satellite, then you've got better temporal resolution. But it's also more costly. So that's maybe the main reason why we can't do it yet.
Mhm. So I guess my last question is kind of like, how is this project like different from other projects that are already in progress at NASA? I mean, I don't actually know all of the projects that NASA has, but I would imagine that they do have orbiting satellite telescopes. So I guess
Mhm.
what is special about your project here?
Yeah, so T-Rex's unique capability is the ability to capture movies in the millimeter wavelength. So there is no existing observational facility, either on the ground or in space, that is able to capture movies of the night sky in at around 3 millimeters. And why would anyone care? Because at around 3 millimeters, a lot of interesting things happen. Black holes have accretion disks that are bright, that emit a lot of light at around 3 millimeters. Tidal disruption events, where black holes capture other stars, are visible, are bright at those observing frequencies. So there's a lot of interesting stuff that's happening at those particular observing frequencies. Now the question is, why hasn't anyone done this yet? There are several competing mission concepts, most notably the Black Hole Explorer mission, which is being proposed by Harvard and MIT, which seeks to capture the first image of the photon ring of a black hole from space. But BEX, the Black Hole Explorer, would be unable to capture a movie of Sagittarius A star simply because it doesn't have that capability. It doesn't have the temporal resolution, or it's a completely different mission design. It's a single satellite as opposed to three. Does that answer your question,
Yeah.
Aspen?
Yeah,
Okay.
absolutely. Thank you.
Yeah. Do we have any other questions? Any? Not. It's, I'm all good on my end. Um,
Well, thanks everyone for joining.